on the road here. All right, very good. So let us get started. We will have our exam a week from tomorrow. It'll be in this room after the chair seminar, starting at 10:30, and going for an hour and a half. Okay? And the exam covers to go through the material before we started the quantization of the field. So that's lecture notes 1 through 10 and the assignments 1 through 6. Gopi will have your last pub set graded soon, and I'll correct the solutions and post them soon. Okay? We won't have a review session tomorrow because I have a big grant proposal due on Monday, and I'm dying. So we will have one during our usual slot Tuesday after class. Okay, so come with your questions. All right. As I mentioned last time, the exam is open book as long as the book is in paper and not electronic form. Okay. All right. Very good. So last time we started our discussion of interaction of matter with quantum electromagnetic fields, particularly two-level atoms. And to get that going, I wanted to first review something that everyone has to know very well for their exam. So let's just talk about it now anyway, because the connections with the quantized field are important. Let's remember what we've done when thinking about the interaction of light and matter in the so-called semi-classical description. It's called semi-classical because we're treating the matter quantumly, but we're treating the electromagnetic field classically. That's the semi-classical. Okay? So what we did in that case is we said, well, let's imagine this two-level atom, and let's think about a laser, for example. This is an optical transition that is tuned close enough to resonance with some energy difference between two levels. One we'll call the ground state, one we'll call the excited state. And in assuming this is an electric dipole allowed transition, then the interaction Hamiltonian is the interaction of the electric dipole with the electric field. Okay? And our two-level atom here means that the Hamiltonian for the atom is just associated with those two levels. And if we take the ground state here, this lower level, to be zero energy, then the Hamiltonian for the atom is just the energy of the excited state, okay? And then we have the pseudo-spin representation with up and down for ground and excited, and this is the projector on the upper level. That's how it could be expressed in terms of the Pauli operators, right? Okay, so let us remind ourselves of a few things. So the laser is monochromatic, we're taking it to be at this frequency omega, and for simplicity, I'll take it to be linearly polarized. Imagine this was a transition, that was a pi transition along the quantization axis here. Doesn't really matter, those details of atomic physics. There's some allowed transition driven by this, okay? And let's just take the phase of the field at the position of the atom to be zero, okay? Like take the atom at the origin. Doesn't really matter again. So this is the Hamiltonian restricted to this two-level space. Of course, has this form. It has these form where it has only the off-diagonal matrix elements because the states G and E have no permanent dipole moments because of the parity symmetry of the atomic wave function. Okay? And so we had this form, and I decomposed my cosine here into 1/2 e to the minus I omega t plus 1/2 e to the plus I omega t, right? So this piece of the field is what we call the positive frequency component, and this piece of the field is what we call the negative frequency component. And one is just a complex conjugate of the other. And I'm just taking this amplitude to be real. Okay? I didn't have to. I could have absorbed the phase in there and then it would have been conjugate, but it doesn't matter. Okay? So then when re-expressed in terms of the Pauli pseudospin representation, that interaction Hamiltonian could be written as such, okay? Where this energy, h bar capital omega, is the energy associated with the interaction of the induced dipole moment with the amplitude of the field. Okay, and I'm taking that, again, this matrix element to be a real number by a special choice of the wave functions. I can do that. Okay? So this is the Hamiltonian for the two-level approximation. And then if I go to a rotating frame, usually not, I call it a rotating frame as opposed to the rotating frame, because when we, remember when we did the rotating frame in the beginning of the course, we went to a rotating frame rotating at the frequency of the laser. Right? Here I'm going to the frame rotating at the frequency of the atom. Okay? Because I'm going to the interaction picture, just to emphasize a particular point. It's a subtle point, but a particular point. So the interaction picture, for those of you who know it, is the sort of intermediary between the Heisenberg picture and the Schrodinger picture, where the operators evolve according to not the total Hamiltonian, but just the free evolution. In this case, the free evolution is the evolution of the atom. That's the only quantum object in the thing. So in the interaction picture, these atomic operators now evolve according to time, and that's their time dependence when you do that transformation. Okay? So that's in the interaction picture. It's a rotating frame. And if we then look and we expand out, we get these four terms. We get the terms that are what I say near resonant, and the terms that are anti-resonant. So if the laser is tuned very close to this frequency difference in Bohr frequency associated with those energy levels, then this is the detuning, will be tiny compared to the frequency itself, right? Like in an optical transition, that might be, 100 terahertz versus a megahertz, right? Okay, so the detuning is tiny, absolutely tiny, orders and orders and orders of magnitude smaller compared to that frequency. Okay, so my claim is, when that's the case, that if I looked at the time evolution operator, the total time evolution operator, which you will remember is the time-ordered product of the exponentiation of the interaction Hamiltonian in the interaction picture. And those of you who have studied this should review it. It's not essential for those of you who haven't. I'm just making some connections to things that people should know because they studied it with me. Okay? And if you don't want to be mad, you don't like me when I'm mad. All right? So anyway, with that said, this is the time evolution operator in the interaction picture. And so you look at the time integral of these things, and the point is when you integrate these guys in the sort of standard Fermi's golden rule picture where you let t go to infinity, these become integral over all times, which become delta functions. Right? Where you say this has to equal this in order to make a transition, whereas these guys, integrated there's no way to satisfy that. Now that's the sort of extreme version of looking at the time evolution, not in infinite time limit, but in finite time. And when you look at that, you see that the equations of motion are such that these terms contribute tiny amounts to how this problem evolves in time, whereas these contribute very strongly when I'm close to resonance. So the resonant terms dominate over the anti-resonant terms when the detuning is small compared to the frequency itself. Okay? Now, just again to remind you of something what I was just saying, we could talk about this point of view. I mean, what I've done so far, I haven't, other than the two-level approximation, I haven't made an approximation, right? I just rewrote this in a certain picture, and we have that the state of the atom evolves according to time in the interaction picture, according to time evolution, right? That's what quantum mechanics tells us, right? And in the everything is in the interaction picture here. This guy is, the time-ordered e to the minus I, the interaction t prime, dt prime, which is 1 minus I, 0 to t, plus integral 0 to t, dt prime, integral dt double prime, 0 to t prime. This is the so-called Dyson series. So again, I haven't made any approximations yet. I just said this is a way of solving the time evolution, right? And then if we wanted to say, given some initial state and some final state, what is the transition probability for going from that initial state to that final state? Well, the probability to go from some initial state to some final state is whatever the final state of the time evolution operator in we're all the interaction picture squared, right? So this is my size 0, and my final state is whatever I want it to be. Okay? Bless you. So, let us imagine, as we do when we typically think about time-dependent perturbation theory, where we say our initial state has some energy initial. This is an energy eigenstate of H0, in this case H atom. So let's say that this is one of the energy levels of the atom, and this is another energy level. We want to know, so let's say that this guy is H0, this is some EI, and let's say the final state is some E final. They're both energy eigenstates, for example, from ground to excited. I want to know what is the transition probability to go from the ground state to the excited state when I'm driving with the laser. Well, I could do this. We know how to do that. I mean, we solve Rabi oscillations. But I could think about it if I wanted to. I want to compare that because it's going to come to this whole question of what were we talking about with virtual particles and all that stuff. What the heck does that mean? Let's think about it let's think about that transition from the point of view of this picture here. Okay? So, well, if I do that, if these guys are two different states, the initial and final state, then this term contributes to nothing, because it's orthogonal. And then I'm going to have a term, my probability amplitude is going to be something like minus I integral 0 to t, so my transition amplitude from final to initial, my final initial dt prime plus final t prime initial t double prime initial plus dot 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 squared. Okay? So I just looked at the inner product where the initial state was this, and then I want to know the probability amplitude to be in the final state, take the inner product, right? And then each one of these guys, we saw we can look at this, what this is in this case. They're going to have these different, when we plug this in, and this is where I was coming from before, I'm going to have those exponentials here, right? And then we take the usual limit. If we take t goes to infinity, what we'll get, that this is where we get Fermi's golden rule. This is first order perturbation theory. It says in this limit that the time of observation goes to infinity, that this has some delta function in it, where between the omega Eg and the laser frequency. Right? And similarly, over here, where we're going to have something like, well, I have some initial state. I get to the final state through some kind of two-photon light process. And that two-photon light process can also be resonant, right? It'll be something like, there'll be some delta function here with the difference between the initial and the final. In this case, it's an EG. This is initial final. Final initial. Minus twice whatever the laser frequency, for example. That's a two-photon transition, right? Now, this is a big question mark. What the heck are we talking about when the t goes to infinity? Again, let us return to this picture over here. If I were to just ask you, having not going through all this rigmarole over there, I said the following thing. I start in the ground state. I have some laser tuned to somewhere near resonance. And I wanted to ask you, what is the probability defined as an excited state? How would you do it?
Look at the block sphere and look how it's off. You know, doesn't like it.
Exactly. I mean, you would make the rotating wave approximation. And in the rotating wave approximation, we always have Rabi oscillations, right? And when we have Rabi oscillations, we would say that the probability to be in the excited state after, starting in the ground state would be equal to co-squared the generalized Rabi frequency, T over 2, divided by, this is the usual Rabi solution, omega squared over omega squared plus delta squared. That's what we found when we solved this problem. It's exactly as Zeke described it, where we said, here we are, we started this guy, we're detuned by some amount, we Rabi oscillate around this generalized Rabi vector, right? Which is when I'm off resonant. And if it were the case that this was weak, if the Rabi frequency is small, so this is the perturbative solution, would be this would be time t equals 0, it's sine squared. That's in that limit, okay? But even if I'm off resonance, I still have some probability to get into the excited state. There's nothing that forbids that to happen. I mean, if I take the limit that t goes to infinity, then the only way that I see that this thing, becomes a kind of, the sinc squared becomes like a delta function there, right? But there's nothing, I mean, what we know that happens is it just keeps oscillating like that. So this idea that if I absorb a photon, I can only go to the excited state when I'm right on resonance, quantum mechanics doesn't say that. The point here is that this thing evolves in time because it's not an energy eigenstate. If it was an energy eigenstate of the whole system, it wouldn't evolve. It would be a stationary state. The only reason it's evolving is because it's not an energy eigenstate. And if it's not an energy eigenstate, that means it has an uncertainty in energy. So we can't really we could talk about the energy eigenstates associated with the non-interacting Hamiltonian, but that's not the eigenstates of the whole system. The eigenstates of the whole system are the dress states, right? If I started in the dress state, then I'd stay in the dress state. But if I start in the bare states, well, they evolve, okay? So now, of course, if I wanted to do, in some sense, we talk about this in terms of the time energy uncertainty principle, right? That is to say, the probability that I get into the excited state with high probability for a given mismatch in the energy depends on the time of the interaction. Right? So there is this notion that you might say that I can violate energy conservation and go from here to here because of the time energy uncertainty principle. It's one way I think of saying really the same thing, which is to say, I have energy uncertainty. If I have energy uncertainty, well then there are possible energy conditions within that distribution of possible energies that satisfy the situation that we see. Okay, now I want to connect this to what we were talking about last lecture. Let's talk about now the fully quantum description. Not the semi-classical, but the fully quantum. Two-level atom plus quantized field. Okay? So now what I have is the Hamiltonian for the atom, but I also have the Hamiltonian for the field and the interaction between the atom and the field. Okay? Again, we're looking at, or we'll talk about when this is a fair thing to do, situations where the field modes of interest are ones that are close to resonance with my two-level atom. When that's true, I just can take those two levels. Okay? So this will take, as we took before, that's my atomic Hamiltonian, that hasn't changed. My field Hamiltonian here, well, that's the sum over all the modes, whatever those modes are. H bar, omega, K, A dagger, A plus a half. And then we have the atom interacting with the quantized field. Okay? And this is at the position of this. Okay? Again, so this is my atom field interaction. That atom field interaction I can break up as we did before. The atomic dipole is the same as before. It has some decomposition in terms of the Pauli matrices, just as before. And then I have this, which I can break up into the positive frequency component and the negative frequency component. Remember before that was a half E, we had on the board just a little bit ago. Okay? So I'll just write out all those terms. Okay? Those are the four terms. Right? Now what are E plus and E minus? Those are the positive and negative frequency components of the quantized field, which we wrote in a normal mode decomposition. Okay? So E plus is equal to the sum over the modes, square root of 2 pi h bar omega A K U at position R. Okay, that could be a plane wave. This could be, for example, either the IK dot R over the square root of the volume. Yeah.
So, you know, the
Time.
special, is that where you, like how you do your notes, where you absorb the polarization into the spatial node?
Yeah.
Okay, is that, okay.
Yep, indeed. So this is my U.
Okay. Oops, well,
Yep, sorry. I'm sorry, I just noticed that I forgot to write that down. Now, I just, one very subtle point. You may remember from the lecture and in the notes, there's actually an I out front here. That's when we quantized the field, we wrote the vector potential first, and then when we took the time derivative of the vector potential, that brought out an I here. And now I'm not writing that I. Am I allowed to do that? The answer is yes, I am. The reason is, I mean, where I can replace A, all the A's by I times A, and all the A daggers by minus I times A dagger. And that won't change a thing. It's a redefinition of what we mean by it. And it's just, there's no reason to drag that I around. So you'll see it both ways in the literature, just as a point of view. Yeah.
Is it kind of like if I actually did, you put that operator on state, I would just have an overall I phase?
That's correct.
So you could just, okay, okay.
Okay, so with that definition, what I see is the following. The atom field interaction Hamiltonian has the following form. The sum over the modes, H bar K U, sigma plus sigma minus times H bar G U A K U dagger plus G star. Okay, where H bar G sub K mu is equal to the dipole matrix element dotted into the mode So what is this constant G? This constant G is the quantum analog of the Rabi frequency. Right? This is like the electric field of the photon. Right? At the position of the atom, dotted into that. It's actually, remember, there's this factor of 2, because remember we had a half over there. Stupid factor 2 is there. We'll come back to it. Okay, so now let's look at this again. This looks just like what we had before, right, for the classical. Remember, this was like everything that went. So now let's go to the interaction picture. In the interaction picture, the operators evolve according to the free evolution. So the interaction Hamiltonian in the interaction picture is now sum over k mu e to the plus I omega e gt plus e to the minus h bar g. A evolves like e to the minus I omega t, and this guy evolves according to e to the plus I omega kt. And as before, we have the resonant terms and the anti-resonant terms, right? Except the only difference is that we have these A's and A daggers. Before we didn't have those A's and A daggers because those were classical amplitudes, right? So we will have terms that look like A sigma plus e to the minus I omega k minus omega e gt plus a dagger sigma minus and then we have terms that ak sigma minus e to the minus I omega k plus omega e g t and a dagger sigma plus. Sorry for this horrible board work. Okay, so those are the four terms. Now, again, if I wanted to ask the following question, I start with some initial quantum state of the system. This quantum state is a quantum state that's a joint state of the atom and the field. And so I start with some initial state. And I want to know it goes to some final state. Okay? I could ask if I want to suppose this initial state was an eigenstate of the free Hamiltonian, the Hamiltonian without interaction. For example, it might be atom in the ground state and some number of photons in all the modes. That might be my initial state. Or it might be the atom in the excited state. And so if these are examples of eigenstates of the free Hamiltonian, the non-interacting case. And then I have some final states. For example, that might be atom in this with some other, an excited state with some other numbers of photons in the modes. I can ask, what is the probability amplitude? And therefore, what is the probability to go from the initial to final state? And the way I would do it is I would do that. That's what I would do. And again, I have this, I could express that in terms of the time-ordered exponential of the Hamiltonian. and do the same Taylor series expansion that I did before. And I would look at the possible transitions between some initial states to some final states. Now, what we see here in that is that the Hamiltonian, not the unitary, but the Hamiltonian has these, pieces in it, right? These pieces that have to do with annihilating or creating photons and taking the atom from the ground state to the excited state, or taking the atom from the excited state to the ground state. Those pieces of the Hamiltonian are what we call elementary processes. They're terms in the Hamiltonian. So we have, for example, terms that involve annihilating a photon and raising the atom, right? And we wrote that as a Feynman diagram, where we said this represents the ground state and this thick line represents the excited state, and a arrow into that is the absorption of a photon. So associated with each one of these terms in the Hamiltonian, we associate a Feynman diagram. Similarly, I could have the opposite, where I create a photon and go from the excited state to the ground state. And this involves emitting a photon. And then we have other elementary processes, processes which correspond to absorbing a photon, but going from the ground state to the excited state. Right? And we have the conjugate one. Where I go from the ground state to the excited state, and I emit a photon. All those are possible elementary processes that exist in the Hamiltonian. But the question is, how do they contribute to, yes, the evolution?
In the third figure, do you have just the diagrams for the grounds and the excited switch? Because I thought the thicker one was the excited.
Oh yeah, I'm sorry, this should say E, and this should be G, sorry. That's sigma minus. Yes. Thank you. So, what we saw here is that when we expand this, we had terms that involve, for example, there's the first order guy, which would be the kind of thing we wrote down just a moment ago. And then we have second order terms. Which will involve two integrals, right, of the Hamiltonian, just like we had before, right? And then we square it. So now, here is the point. If we take the initial state to be one of the eigenstates of the free Hamiltonian, and the final state to be some other eigenstate of the free Hamiltonian, and we ask, what is the transition amplitude from here to here? Well, it evolves. But if we go to the limit that t goes to infinity, and we go to the Fermi's golden rule kind of limit, well, then there's no way to satisfy energy conservation with the off-resonant terms. Only these terms contribute. However, if I am not in that infinite time Fermi's golden rule limit, well, then these terms do contribute. They just don't contribute a lot. And the degree to which they contribute depends on this time. Okay? And that's why we make this kind of time energy uncertainty picture says, well, I can do this kind of thing and violate energy conservation virtually. That's the language that's used. However, I would say that, I'm just not comfortable with that. I don't know what that really means. All I know is that this is what happens, and the system is not in an eigenstate of this sort. These are the eigenstates of the free Hamiltonian. If we started in such a state, that is not an eigenstate. We have energy, so it means there's probability amplitudes for all these other things. They're just small. Okay? Now, there are contributions of this that are energy conserving in higher order. For example, so what we have is that the resonant terms are dominant in first order. And those are the terms that look like A sigma plus and A dagger sigma minus. Right? But in second order, we can have the following kind of thing that totally conserves energy, where I start in the ground state with no photons. I end in the ground state with no photons. Intermediately, I have a photon and an excited state. So this is E1. But at the end of the day, energy is conserved. Okay? This is a possible process which would satisfy the Fermi golden rule type energy conservation, but in second order.
So is the energy conserved only at
The beginning and the end.
It's not in between though. Like
So
while the process
here is a question for you. At the initial time, what was the energy? Well, the energy is uncertain. I could say there's the expected value of the energy. This guy is an eigenstate of the free, right? So its energy is that for the free, but it's not the definite energy of the system, because if the energy was absolutely definite, nothing would happen. It would be a stationary state of the universe. So the only reason something happens is because it's not an eigenstate of the Hamiltonian, of the whole Hamiltonian, including the interaction. Now, if I want to talk about the free, the energy, in this case, so a way that people talk about it is to say, well, the energy was this at the beginning, it was that at the end, and intermediately, we didn't conserve energy, but that was okay because of the time energy uncertainty principle. You decide whether that's a good way of interpreting what's happening or not.
If at infinity, energy is conserved, but as you start shrinking that 0 to t, and you take a measurement where you're emitted a photon and went to the excited state, where does that energy go or come from?
That's a good question. That's a very good question. Energy is always conserved. energy comes from somewhere, right? So the point is, I would say, is that the energy is in the system there, always. There's some probability amplitude. If it wasn't, as I'm saying, in this situation, there was some probability amplitude for the system to have this total energy. It was always there. Now, how you know, if you measure and you see something, does the measurement in some way, you know, you have to take the measuring device into account, right? I mean, that's also part of the whole description of everything. But I would say in this picture, if I have no measuring device, this picture is consistent with energy conservation because there was always some probability amplitude to have that energy, right? If I decomposed the whole system into the dress states, I would find there's some amplitude to have the photon and the atom in the excited state. It's just a very tiny amplitude. Now what that means, of course, is that the energy of the ground state is not the free energy of the ground state. It's the dressed energy of the ground state, dressed by the vacuum. The vacuum itself perturbs not just spontaneous emission of the excited state, but the energy of the ground state. Okay? This is a contribution to what's known as the Lamb shift. It's not the whole Lamb shift because, of course, you know, we've made the non-relativistic approximation, we've made the rotating wave approximation, we've made the two-level approximation. But the Lamb shift is the shift in the energy level of atoms that's due to the vacuum. Okay? That's why the light shift is sometimes called the lamp shift. And you see, we remember the light shift when we talked about the light shift for when we put real light, a lamp, on it. We could think about that as a two-level process, right? Where we have both, we start in the excited ground state and then we go back. This is a allowed transition because this is, you know, I absorb a photon, but then I re-emit it back, stimulate it back. That's this kind of process. Okay. So one of the things that we learned here, and this is just a baby introduction to the whole theory of Feynman diagrams, is that Feynman diagrams are expressions of perturbation theory. They're just diagrammatic ways to look at the different terms in the Dyson expansion. That's what they are. Whether you want to associate physical reality to these processes, maybe. But it's a way of expressing, thinking about calculating dynamics, and particularly calculating scattering cross-sections, which is what high-energy physicists only ever measure in their colliders, through thinking about these elementary processes. The difference between what we've done here and what you would do in high-energy quantum electrodynamics is that you would treat the charges relativistically. And when you treat the charges relativistically, you can't just talk about the electron, you have to also talk about the anti-electron, also known as the positron. And the elementary processes there don't correspond to absorption emission to different band energy levels, but processes whereby electron scatters with positrons and photons. You'll have this same kind of 3-point, but now you'll have electron, positron, and photon. Yeah, so I had some questions around. Yes, Z?
So, you know, those four processes.
Yep.
Let's say I have a detector and I detect a photon.
Yep.
I really don't know which process it was, right? Like, I don't know if it went excited to ground to excited. I mean, I know which was more likely.
Yeah, you can't say for sure.
Okay.
I mean, you can predict with more probability. If you prepare an atom
Okay.
in the ground state, you know by doing some other measurement that you prepared the atom in the ground state, and then you look for, as was suggested, this thing,
Yeah.
you would know that this happened.
Okay.
Right?
And so, I mean, I'm looking at the math, I'm trying to think, I mean, again, the amplitudes are small, but they would interfere too with each other, but, I mean, it's just small.
Exactly.
Okay.
Yeah. And, you know, when one does in high energy physics, one tries to calculate as many of these diagrams as possible. I mean, that's what, old time phenomenologists, people who would take, QED expressions and calculate as many Feynman diagrams as possible to calculate the corrections to, the mass of the electron and stuff like that. There aren't any interference between these, because these are amplitudes. They're not probabilities. Yes?
Two questions.
Yep.
In the case where, in the non-intuitive cases,
Yeah.
where there is a radiation, even
Yeah.
though you don't think it is, what is the frequency of gamma? Because generally we associate the difference between the
Yeah.
energy eigenstates to that.
Sure.
And then the same thing with the other one where we have detuning. And I guess I know the answer to that one, because when you have detuning, and even then if you see some light, it's probably still the same frequency. Does the question make sense?
So I would say a few different things. Let's first talk about the classical cases where you're saying this, right?
Yeah.
So, if I start the atom in the ground state and I apply the laser light for some amount of time, there's some probability to find an excited state. So we just wrote down. When we find it in that state, it has energy different from the energy of the photon. Where did that energy come from?
Well, I mean, like, again, isn't it this, the whole thing where, like, we're perturbing the excited and ground states with the field that become dress states, so it becomes superposition of excited and ground. So it was maybe there?
Yeah, I mean, there's a few different ways of saying the same thing. If I apply this for some finite amount of time, it wasn't a monochromatic field. It had a spread in frequencies. And that spread in frequencies is inversely related to the time, right? That's an expression of the time energy on certain, it's just Fourier analysis, right? So the fact that after some finite time I see this is totally consistent with it, that a photon disappeared with that frequency with one of these, because it was that frequency, right? This is the one that, okay? Now, in the quantum case, at the moment, I haven't said where this frequency associated with this K comes from at all. It's a little, I've swept this under the rug at the moment. And I just said, let's just talk about the interaction of the quantized field with this two-level system, okay? Now, in this kind of case, really, it has to be all the frequencies, because there's nothing resonant about it, so it's all of them. And that's one of the reasons that I was saying that this is not really the whole Lamb shift, because if I'm using all frequencies, well then, I can't talk about the two-level approximation. And I can't talk about the rotating wave approximation anymore. So to really calculate the Lamb shift properly, I need to do the full QED, including the positrons and everything, to get that right. I think you had a question?
Yeah, just in kind of an analogy with QED.
Yeah.
With the creation and annihilation and the sigma plus and sigma minus be like vertex factors?
Exactly. These are Feynman diagrams. They're not analogies to Feynman diagrams. They are Feynman diagrams. But they're the Feynman diagrams associated with the Hamiltonian where we've treated the matter non-relativistically, and where the photon energies are low energy. These are not gamma ray photons. These are or high energy UV or X-ray. We're thinking about them as optical photons, or maybe even microwave photons, infrared photons. So these are the vertex terms, right? And as I was saying, the only difference would be that your elementary processes in the relativistic theory would involve creation annihilation of photons that are coupled to creation annihilations of positrons and electrons. Okay? So you can think about quantum optics as low energy quantum electrodynamics. That's what it is. And until Glauber, no one thought about that. Because QED was high energy, but not low energy. The reason that you can have quantum and low energy is because photons are relativistic no matter what the energy is. So it can be low energy, but still relativistic. All right, all good. This was fun to see. So we get a little bit of taste of what that's all about. All right. So, now let us look at a very specific and very important example. We're going to look at the case of the interaction of a two-level atom with one mode of the quantized field. Okay? Yeah, well, I mean, these are the normal modes. They're the spatial modes, right? Now, when is this, what context? I mean, you know, the quantized electromagnetic field, all modes are possible. So when would it be possible to talk about the interaction with just one of them?
Laser?
We could, for example. But in particular, what we're going to look at is what's known as cavity quantum electrodynamics. Last year. Cavity QED. So, as you suggested, Zeke, let's imagine I have a laser cavity. It's a Fabry-Perot cavity. Okay, there are lots of modes in here. You know, they have some transverse modes, TEM, whatever's, and then there's some longitudinal, depending on, right, there's some particular mode of this, and has some polarization. Let's suppose, so there's some cavity mode. There are an infinite number of them, but they're discrete. And let's suppose that that cavity mode has some frequency, the mode of the cavity. Okay. So that's the mode where they all fits the boundary conditions. Right? It has that. It's a normal mode. It has some spatial characteristics. Okay. I mean, it's like a whatever it is, TEM 00 with, you know, longitudinal quantum number, n equals whatever. It's got, and it's some spatial function. I don't really care. It is what it is. All right? Now, suppose that we have it such that this cavity mode is very close to resonance associated with some atomic transition, okay? So I have a two-level atom, meaning that there's some two levels, ground and excited, and there's some energy difference between them, okay? So this laser cavity, you know, might have some, you know, spectrum of modes, you know, spaced by some amount. So these are the cavity modes. And here's a particular one, omega c. If I tune this cavity such that the atomic resonance is very close to one of these modes. These modes, of course, have a finite width due to the fact that light can leak out of the cavity. They have finite. There's a finesse of the cavity, a Q, quality factor of the cavity. So much, right? But as long as the separation field is big enough, I could say that really the system only couples to that mode and no other mode. And that's true for the vacuum fluctuations as well. The vacuum fluctuations associated with these other modes are so far off resonance, they don't matter. So when that is the case, if I have a very narrow cavity resonances such that they don't overlap very much, and one of the atomic resonance is very close to that, then I can do this. And that is the realm of what's known as cavity quantum electrodynamics, cavity QED, changing the quantum electrodynamics through the boundary conditions. Okay? Now this doesn't have to be a laser cavity. It could also be a microwave cavity, where the difference between this is a microwave frequency. For example, so this could be, well, I'll come back to that in a moment. Let me just lay out the problem for a moment. So if I do that, I would write down the Hamiltonian for the system. The Hamiltonian for my two-level atom, the Hamiltonian for the field, and the Hamiltonian of the interaction. Okay. The Hamiltonian of the atom is equal to, again, if I take the excited state to be, the ground state to be 0, that's just as we had it before, right? Just another way of writing that. Say for the ground state to be 0 energy. My field Hamiltonian is just the energy associated with that one mode. And I'll just call that, I won't put a label on it, it's just that. And I can put the plus a half in there, but typically we just ignore that, because as we said, it doesn't play any role in the dynamics. In this case, it's just one mode, it's not even infinity. So it doesn't really matter whether it's 0 or you can put it there or not, it doesn't make a difference. And what about our atom field interaction? Well, we just wrote that down. That's equal to h bar g, or was sigma plus sigma minus h bar g a plus h bar g a dagger, where G, H bar G, is equal to the square root of H 2 pi H bar omega cavity times U dotted into the dipole matrix element for that mode at the position of the atom. And we'll take this to be it's cosine.
Is the second G supposed to be conjugated?
It generally would be, you're right. But as I said, you can choose these modes to be real in this case. They're like cosines, right? They generally would, you're right though, it would be conjugated. Okay, so that's it. And if I make the rotating wave approximation, I get the following Hamiltonian. Okay? So this is in the rotating wave approximation, which was valid when we have the case, the rotating wave approximation is valid when the difference between the cavity frequency and the atomic frequency is tiny compared to the cavity frequency, and also that G is much, much smaller than that. All right, so this is a very nice and simple Hamiltonian that describes the interaction of matter with the field, quantized field, in the situation where we just have one mode. And this is known as the Jaynes-Cummings Hamiltonian. Jaynes and whoever Cummings was, or Cummings, I don't know who he was, but I know that Jaynes model. They wrote this down back in the 1960s, I think. And it's one we can solve exactly. Yeah?
The A's and the sigmas are acting on different things.
Indeed, indeed. So let us talk about what is the Hilbert space?
The excited tensor, or the Hilbert space excited ground tensored with just that, the number of space of that one.
Exactly, exactly. So my Hilbert space for the atom and field is the tensor product of the Hilbert space of the atom with the Hilbert space of the field. There's two different degrees of freedom. Each degree of freedom has its own Hilbert space. If I have a two-level atom, that space is spanned by ground and excited. It's a two-level Hilbert space. It's the space of the qubit that we've talked about before. It's on the block sphere. Okay. This is the infinite dimensional Hilbert space that is associated with square normalizable functions on the line. It's this Hilbert space of the harmonic oscillator. It is spanned by the photon number states, the photon Fock space. So when we do this, we can think about the total Hilbert space as being spanned by the set that we write like this, where this is just a shorthand for G tensor N, and this is a shorthand for E tensor n. N goes from 0 to infinity. Okay, thank you, Paul, for reminding me that I need to talk about that. Right? So, this is a problem we can solve exactly. And it's a very rich system. It's a system that plays an increasing role in many areas of physics, not just in traditional atomic, molecular, optical physics, increasingly in condensed matter, solid state systems as well. Because it is the physics of a two-level quantum system interacting with a harmonic oscillator. It could describe this system where the two-level system is an atom and the oscillator is a normal mode of the electromagnetic field. It could be talking about, for example, a string of ions where the harmonic oscillator is the normal modes of motion of those ions and the two-level atom are the internal states of the ions. It could talk about a Josephson junction which has different levels of the macroscopic current in a superconducting circuit that couples to the microwaves in a strip line resonator. That's something that people now call circuit QED, where the quantized no-sheet levels of the currents in the circuit are quantized. These things that we never would think of as quantum objects, they're the lowest of lowest energies. We're talking, how can I even worry about QED when I'm talking about microwave photons and macroscopic currents? So this is a ubiquitous one. In fact, I'm writing my grant folder right now all about this yet again in a whole nother context. So what we're going to do next time is solve the problem exactly.